Hey there, in this video we're going to continue our discussion of antiderivatives, and this is part 3 of our video series for antiderivatives. So here we want to find the antiderivative of this function 3 to the x minus 3 over x we have initial conditions. We have 2, f of 1 is equal to 2 and f of negative 1 is equal to 1. So let's go through finding the antiderivative. So we may need to remind ourselves, when you have an exponential, what do we do? Right, so if you're taking the derivative, right, if you have b to the x and you're taking the derivative, what's the derivative? You get the exponential back, so it's b to the x times the natural log of the base. So we're going backwards. So when you're doing the antiderivative, you do the opposite, right? So the antiderivative of b to the x, the antiderivative, then you're going to get the exponential back, so you're going to get b to the x, but then instead of multiplying by the natural log of b, you're going to divide by the natural log of the base. So going back over here, this is our f of x equals 3 to the x. Notice that now I'm not using the f prime notation anymore to say this is the derivative. We're just, when you're told find the antiderivative of, that means that this is the derivative of something. And oftentimes, the antiderivative is like big capital F. So we can say then big capital F is going to be the antiderivative of 3 to the x. So based on this, the antiderivative of an exponential, we get the exponential back divided by the natural log of the base. So I'm going to get 3 to the x divided by the natural log of the base. The base is 3 minus 3, and then you can think of this 3 over x as 3 times 1 over x, and so that means that this is then 3 natural log of, remember the absolute value, natural log of absolute value of x plus a constant. So this is our function. So the initial conditions are oftentimes given so that we can find the constant. So I want f of 1 is equal to 2. I guess this should have been capital F of 1, capital F of negative 1, right, the antiderivative. So, but this is a little bit interesting because I have, when x is 1, when I plug it in here, right, this is going to be 3 to the 1, but then when it's negative 1, 3 to negative 1. However, the ln of absolute value of x, 1 and negative 1 are going to become just ln of 1. But that's because the natural log of x is absolute value of x, is a piecewise function. Recall, the absolute value of x is equal to x when x is greater than or equal to 0 and is equal to negative x if x is less than 0. So this antiderivative then is a piecewise function because of that absolute value. So how do we write it? So we're going to say then the antiderivative of capital F of x is then equal to, and we're going to have two versions, right? 3 to the x over ln of 3 minus 3 ln of x. We can drop the absolute value plus, let's say, c1 when x is greater than or equal to 0. Using our definition of the absolute value of x, right? The absolute value of x is x when x is greater than or equal to 0. So ln of absolute value of x will just be ln of x. And then 3 to the x over natural log of 3 minus 3 natural log of, when x is less than 0, natural log of negative x plus c2 when x is less than 0. I know you're concerned, you're like, wait, why? I thought you couldn't have a negative. We don't, right? Negative x. X is less than 0, so that means x is a negative number already. Like x could be like negative 3. So then you have natural log of negative and negative 3, which will be actually be positive 3. So we're just using the definition of the absolute value of x as a piecewise function to rewrite this then as a piecewise function. And now we can use our initial conditions. Our initial conditions were that f of 1 is equal to 2 and f of negative 1 is equal to 1. So let me copy those. So here are our initial conditions. So when x is 1, f of x is equal to 2. So we're going to have, when x is 1, right, f of 1, that's positive, 1 is positive, so we're going to be looking at the top function. So we're going to have 2 then is equal to 3 to the 1 over ln of 3 minus 3 ln of 1 plus c1. And this is 0, so we're going to have 2 is equal to just 3 over natural log of 3 plus c1. So that tells us that c1 is 2 minus 3 over natural log of 3. And now we can use the other one. When x is negative 1, the function value is 1. So when x is negative 1, negative 1 is less than 0, so we're going to be using this function for the second part. And so we can say then that 1, right, f of negative 1 is equal to 1 is 3 to the negative 1 over natural log of 3 minus 3 ln of negative and negative 1, which becomes positive 1, and natural log of 1 is still 0 plus c2. So this tells us that 1 is equal to 3 to the minus 1, which is 1/3, right? So that will be 1 over 3 ln of 3. This is 0 plus c2. So that means c2 is 1 minus 1 over 3 ln of 3. So we get two values of c, and so now you can write your final antiderivative. So f of x then is the piecewise function 3 to the x ln of 3 minus 3 ln of x plus c1. c1 was 2 minus 3 ln of 3, and this is when x is greater than or equal to 0, and then we're going to have 3 to the x ln of 3 minus 3 ln of negative x, and then plus c2. c2 we found it to be 1 minus 1 over 3 ln of 3 when x is less than 0. So in this case we have an antiderivative that is a piecewise function from a derivative that was not a piecewise function, right? But that is because of our natural log of absolute value of x, and given these two conditions. So we had to then look at it as a piecewise function, because otherwise if you plug in f of 1 equals 2, you get one value of c, and then you might be stuck thinking like, well, what do I do with that one? So that is because the antiderivative is actually a piecewise function. All right, let's try our second example. On our second example, we want to find the antiderivative of this function. Right now, in this case, since it says find the antiderivative of, you don't have to have the prime there anymore. It is understood that this is the derivative of something. So we want to find that something. So we have lots of cosecants. Well, not lots. 2 cosecants and 1 sine. Be careful. We don't want to say like, oh, cancel those off. You can't do that. Why not? Because you have a minus here, so you can't cancel over a minus. If you were multiplying, then I can cancel, but we're not multiplying. But remember that cosecant is 1 over sine, is the reciprocal function. So we can write this as, so let's just rewrite before we take the antiderivative, because right now I can't really do much. So cosecant is 1 over sine, so this will be 1 over sine of 2x, right? That's our angle, over cosecant again, so 1 over sine of 2x, and then minus sine of 2x. So this is looking promising, but I have a fraction divided by a fraction, so I have a complex fraction. Let's multiply both sides by the common denominator. Not both sides, top and bottom, by the common denominator. So here, when you multiply this times that, you get that they cancel. So we will just get 1 in the numerator over, and then the denominator distribute. So sine of 2x times 1 over sine of 2x, that's going to cancel. So we'd be left with 1 again in the denominator, minus, and then sine 2x times sine 2x, gives us sine square of 2x. So this looks a little bit better. So I have f of x is 1 over 1 minus sine square 2x, and hopefully this looks familiar, right? We know, what do we know? We know that sine square theta plus cosine square theta equals 1. So that means that if I subtract sine square from both sides, I get 1 minus sine square theta is cosine square. So I can change this to 1 over cosine square theta, which is secant square, not theta, 2x. Keeping my angle the same there. So secant square 2x. So I'm really finding what we want is the antiderivative of secant square of 2x. Right? Notice that here I still have f of x. I'm just rewriting. I haven't done any antiderivatives yet. So now I can take the antiderivative of secant square. So when you see secant square, what function gives you a derivative of secant square? Tangent. So the antiderivative of secant square of stuff, so we have to use a little bit of chain rule here. So my antiderivative, capital F of x, will be tangent of 2x. So what happens when I take the derivative? The derivative of tangent is secant square 2x, but by chain rule I'm going to have times the derivative of the inside, which is 2. We don't have that here, so that means that we need to divide by 2 and then plus a constant. Now when I take the derivative, that 2 and the bottom 2 will cancel, giving me just the secant square that I have. So here, whenever you have the chain rule that you multiply by a constant in the derivative, that means in the antiderivative you divide by that constant. So this will be our antiderivative. So for f of x equals cosecant 2x over cosecant 2x minus sine 2x, right? The antiderivative is capital F of x equals tangent of 2x over 2 plus c. So that will be the antiderivative. Let's try our next example. Our next example is find the antiderivative of tangent square of x. Okay, so lots of trig functions. So this might be a good time to remind yourself of what your trig derivatives are, and most importantly now in this section, what the antiderivatives are. So let's write some of our antiderivatives over here. So if I put the derivative on the left side, and then we're going to find the antiderivative. So let's go over our trig functions. So the antiderivative of sine x, it will be negative cosine x, right? And by checking it, take the derivative of this side. The derivative of cosine is negative sine. So negative and negative will become positive. The antiderivative of cosine is sine. And what else do we know? The antiderivative of secant square x is tangent x. What about cosecant square x? The antiderivative of cosecant will be negative cotangent. And so essentially you're going backwards, so put your derivatives here. So if you have secant x tangent x, what gave you this derivative? It will be secant. And if you have cosecant cotangent, then the antiderivative is negative cosecant. And you can kind of keep going down the line, right? Like what are your antiderivatives you should know? The antiderivative of 1 over x is natural log absolute value of x. What else? Antiderivative of e to the x is e to the x. If you want, you can even put your general power rule here. And you can put the exponential. We did the exponential in the previous example. If you have b to the x, the antiderivative of b to the x is you get the exponential back divided by the natural log of the base. And so you can kind of start listing some of the antiderivatives that you should know. Now notice here, tangent square is not one of these nice, just looking at it, antiderivatives. So what do? I don't have anything right now to use to undo a chain rule or composition of functions. So what we're going to do then is bring in our trig identities. So let's use trig identities. Can you think of a trig identity that we can use here? I have a hard time remembering my trig identities. The one that I do remember is the sine square plus cosine square is 1. And so I just kind of base everything else from here. So if I want to get a tangent square, I know tangent is sine over cosine. So I want to get sine over cosine. So that means I'm going to divide everything by cosine square so that I can get tangent. So when you divide everything by cosine square, you get tangent square, which is what I want. Cosine square over cosine square is 1, and 1 over cosine is secant square. So that means that tangent square theta is secant square theta minus 1. If you remember it, great, that saves you some time. But if you don't remember it, and sometimes there's so many trig identities that you're like, which one do I use? And sometimes we create anxiety for ourselves trying to just to remember, instead of just like, okay, like for me, I used to have a lot of anxiety trying to remember all my trig identities. So one day it just clicked like, oh, if I just remember the main one, sine square plus cosine square equals 1, then whatever I need, if I need a tangent square, divide by cosine. If I needed a cosecant square, divide by sine. And so things like that just kind of, at some point that clicked and it reduced the trig identity anxiety. All right, so then my tangent square is secant square theta minus 1. So we want to find the antiderivative of tangent square x. So I know f of x is tangent square x. So that means I can rewrite this using that trig identity that I just found by saying, well, tangent square is secant square theta, x minus 1. And I know the antiderivative of secant square is tangent. So then my antiderivative is going to be capital F of x will be the antiderivative of secant square, which is tangent x, and then the antiderivative of 1, which is x, and then always plus a constant. And that's that. So here the tricky thing was remembering the identity for tangent square x. Well, first, I guess recognizing that you can't just take the antiderivative of tangent square. It's not one of the ones that gives me a function right away, so I have to rewrite it. How do I rewrite it? I have to use trig identities. Which trig identity? You know, the one that gives you tangent square equals something. If you don't remember it, derive it, and then take the antiderivative. And now our last example, find the antiderivative of this function. So at first glance, it looks like this looks a little messy, so we want to rewrite that. If you can rewrite it, always rewrite your problems and to make them a little easier. So we're going to rewrite f of x to be sine x. It's just a single denominator there, so I can split up the top fraction. So I'm going to have minus 2x cubed over x, and I am splitting, so plus e over x, but I'm really subtracting it. Or we can put parentheses so that we don't forget. So plus e over x. And I'm still rewriting, so this will be sine x minus 2x squared, and now we don't remember that to distribute that negative minus e, and I'm going to write that times 1 over x. Now here, remember, I don't want to do e times x to the minus 1, because as soon as I see 1 over x, we should recognize that the antiderivative of that is ln of absolute value of x. So we don't want to use the general power rule on 1 over x, because its antiderivative is a very specific function, the natural log of x. So I'm just still rewriting here. Now I can take the antiderivative. So it'll be capital F of x, or whatever notation you want to use. The antiderivative of sine x. So we just wrote all our antiderivatives up here. The antiderivative of sine x is negative cosine x. So the antiderivative here will be negative cosine x, and then here I can use the general power rule, so it will be minus 2x to the third over 3, right? Add 1 to the exponent, divide by the new power, minus, or plus, no, minus, e times the antiderivative of 1 over x. Now, e is just a constant in this case. This is not e to the x, so the e is just the number 2.718. So this is going to remain a constant, so e times the natural log of absolute value of x plus a constant. And here I don't have to worry about this being a piecewise function. If I was given an initial condition, now I have to worry about it because the absolute value of x is a piecewise function. And so that will be our antiderivative. All right, email me if you have any questions.